All right, guys, we're moving on to some good stat stuff for Unit 5. So this will lead us up to our last little bit and then the final project, which we do at the end of the year. Okay, so let's look at first 5.1, which is going to look at some one variable stats. So one variable stats means we're looking at one thing, just one piece of data. So we're not comparing things. Later on, we're going to do two variable analysis where we're going to say, how does this compare to that? Does this influence that? That sort of thing. But today we're just going to look at one variable stats. And I think we're going to start off with stuff you already know about, which is things called the measures of central tendency. So we have the mean, which is just the average. So you take all the data and divide by the number of data points to get the average. The median and the mode. So those always go together, right? So those are the measurements of central tendency. The median is the middle value. Okay. If there's two middle values, take the average of the two middle values. So here, if we have this 5, 9, 7, 13, 11, 15, put them in order like this, right here. And then the two middle guys are 9 and 11, and the average of 9 and 11 is 10. So that's how you get that. And mode is the most common. So if you look at the mode, so if you have a bunch of data points and they're not all unique, if they're all unique, then there's no mode. But if there is a if there's repetition, then the guy who's repeated the most is your mode. So looking here, sorry guys, my fault. This is rolling dice. So when we look at the dice, the most common thing to come up is this, rolling two dice, the most common thing to come up is the 7. So it's the mode. The mode interval is very similar to mode, except that in this case, we're not looking at specific data points, but we're looking at a range or an interval of data points. So if you have things like this, scores in the 90s, the 80s, the 70s, the 60s, all the way through, which one is repeated the most common is scores in the 70s. So that will be the modal interval. So it's the mode, but it's not an actual number. It's an interval. So you can go ahead and take a look at how to do these things on sheets. So we're going to use this later on. It does a lot of the stuff for you. So neat stuff there. And then that's kind of it, really. When it comes to mean, median, mode. There are differences, though. So if you look at this sort of thing here, life expectancies, you might have mean, median, mode not being the exact same, right? So the median, especially the mode, right? The mode, often, the mode is very useful in some cases, but sometimes it's a little bit off, so, or not really useful. But we will talk a little bit more about what that means as far as what do these guys do, how do they relate to each other, the mean, median, mode. If one's higher than the other, why is that the case? So just give that a bit of a go right now. And then there's a quiz, and that's it for this. So I'm going to keep going with the same video here, because that was quick. So let's go to 5.2, U5A2, and we'll talk more about spread. So this is going to be kind of new stuff here, but still one variable data. So we're only looking at one thing still, and instead of looking at well, let me just do a quick example while we do this. So I have an example. Give me 1 second here. All right. So these are my in-class data notes. So mean, median, mode, we start off with that same thing there, and then we'll get to this stuff in a bit. But then we get to measures of spread. So what an example here is here. So we look here. Sorry, guys, just thinking out loud here. So we get to a situation where there's some basketball players. So there's a bunch of kids here and a bunch of kids here. And the question is, how can we talk about how spread out this data is? So when you look at these kids here, here's team 1, here's team 2. Two basketball teams walk in. You look at the heights here. You have Laura, 183. That's 6 feet tall. You got Colleen Short at 146. You got kids from all over the place, height-wise. On this team here, the Ravens, what you have over here is a group of kids that are similar in height. And if you did the mean median mode, I figured these out. They're all similar. I don't remember exactly the numbers here, but let's say they're all around 163, 163, 163-ish, 164. This one doesn't have a mode. This one does at 166, I believe. So these kids are about the same height, 160. Like as a group, if I look at the central tendencies between the Ravens and the Falcons, these numbers might be a bit low, 165-ish or whatever, but it doesn't matter. What I'm saying is I can't compare these using just mean, median, and mode. Forget about mode, but if I look at the mean and the median, these guys have about the same average height and the same middle height. So the average person is about 165, and the middle person is about 165. So Maria might be the middle person here, and then Jamie might be the middle person here. And they are the same height, right? But then when you look at them, Laura's taller, Ingrid's taller, Justice is taller. Here you get some kids that are a bit taller, but they're barely taller, right? They're 166, 168. That's, 3 centimeters. That's like an inch, right? 2.5 centimeters to an inch. So this group of kids this team here is more consistent in height, right? So we don't have a measurement when you look at mean, median, mode that will work there because we're looking at central tendency. That is the stuff, I don't want to say the middle because the middle is the median, right? So you get the middle, then you have the average, right? Which is the mean. So you have the median, which is the middle, the mean, which is the average. You have the stuff in the center, but we don't look at extremes. We don't look at how, not even extremes. We just don't look at how spread out this is. This isn't really extreme. Jamie is no more common in height on this team than anyone else, right? Because they're all over the place, right? You got this kid, that kid, these two are shorter, right? These two are taller, like I said. Here, the person in the middle is similar in height to the people on that are taller and shorter than she is. So what that means is we need more information, right? And what we do is a couple things. One is range. So range is very simple. All you do is you take the biggest person and subtract from it the shortest person. So you take the big data. So here 183, 146, and you subtract those here and you get 37. So 37 is the range of the data here. This range here is 168 to 161. So a lot of times students just like to write this is the range. And I understand why you do that. That is the range of data. But when we ask for the range, I actually want this, the calculations, the difference. Okay. So 7 centimeters would be the range. So sure, this is great. That has a bigger range than that. But I guess you can probably think about this for a second. Here, let's look at this team and let's look at that team. Let's make a new team, right? That's 183 and 146. But then everyone else is about the same. 166, 166, 164, 163, 165. Okay. So in this case, you have a really short and a really tall person. Okay. And then everyone else is in the middle. That's a different group than this team, right? So we need a way to express that. And what we do is we do something called standard deviation. So I'm going to show you how to do that by hand. You're not going to have to do it by hand, but I do want to show you how to do it. So what you do is you take, the first thing we're going to do is we're going to take the average height. So I'm going to do this for the Falcons. And you take the average height of the team, of the data. So in this case, it's 165. The other thing you need is how many data points are there. And in this case, we call that N usually. And in this case, we call N is 7 because there's 7 kids there. So 165 is our median. Our mean. And N is 7. And then from there, we calculate the standard deviation. First, we calculate what's called the variance, then the standard deviation. To do this, you take the data point, any data point. So that was the first kid's height, right? So you take all the data points, all these here, and you write them out like this. I like to do it in a table form. You can do it as an equation, but if you do it this way, I think it's a little easier. And what you do is you take the 183 and you subtract from it the mean, 165, and then you square it. So the reason we square it is this is going to give us the difference between the data point and the mean. But if we take all the differences, what you're going to find is some of the differences are smaller and some are bigger. So if our mean's 165, you would have 148 is going to be less than that. So it'd be like minus 17, right? Away from the mean. 183 is pretty much the same size, but the other way around. It's plus 18 centimeters bigger. And if I was just to add these together, what I would get is 1, which would mean that if we don't square these guys are going to cancel each other out. The 17 and the 18 kind of cancel each other out because if I said just add up all the differences, you can have positive differences and negative differences, and they should be about the same because that's how you get the mean, right? Think about it. It's in the middle. Anyway, what we do instead is we square it, because when you square a number, you do a couple things. One, the main thing you do is you get rid of the sign. So if negative 17 is way over here and 18 is over here, I don't really care about is it bigger or smaller. I do care about the size or the magnitude. So to get rid of the sign, there's 2 ways you can get rid of the sign in math. One is to put this thing around it, which is just 2 straight lines, which is called absolute value. And that would just turn this into 17. We don't do that in this case, okay? What we do instead is we square it. And another reason I think we square it is because when you square a number, numbers get much bigger if they're bigger when they're squared. That was horribly said, but let me show you something. If I have 2 and I have 3, and I'm 2 away and 3 away from the data, and I square them, so 2 and 3 are one away from each other. But if I square these, I end up with 4 and 9. And the square of 2 and 3 has a bigger difference than 2 and 3 themselves. So what I'm saying here is, for standard deviation, the numbers that are further away from the mean are going to now have a bigger input and a bigger contribution to what we do at the end here, which is add up all the differences. Okay, so that's why we do it. Let me explain what we do. If you didn't like that, that's fine. But let me explain what we do. You take the point, you subtract it from the mean, and you square it. So that, subtract that, squared, 324. In this case, that is the mean. So 165 subtract 165 squared is 0. This one here, and I don't do all this. What I would ask you to do is to do this on your calculator. So you go 148 minus 165, leave it on your calculator, square it, 289. Square this, square the difference, square the difference, square the difference, square all the differences, right? So this one here is 154, subtract 165, squared. So that's minus 11, square it. It's going to turn into positive. Add all these up, you get 1520. The sum, okay, so the sum of the differences is 1520. What we call the variance is the 1520 divided by n. So that's your variance. And if you get the square root, that's your standard deviation. So sigma, little sigma, big sigma means added up. Sum, little sigma means standard deviation. Little sigma in this case is 14.7. 14.7 is a value which would have the same units, centimeters here. Now, we're going to talk later what that means. In this case, all we care about is this. If that's 14.7, a bigger standard deviation means more spread, right? These numbers are bigger. If these numbers were closer, so if we were to do this for the Ravens, all these numbers would be smaller. You add them up, that's a smaller number. You divide by 7, that's even a smaller number. You take the square root, it's even a smaller number. All we care about right now is that the Raven standard deviation would be less than 14.7. Bigger standard deviation, more spread out. Smaller standard deviation, less spread out. Okay, so that's the extent really of what you need to know for this part of the unit. You can look at interquartile range. We'll get into that a bit later. So all the stuff you're going to do on Google Sheets. So learn how to do, find the quartiles here, and then learn how to find standard deviation there also. I have a little video here that goes over standard deviation a little bit further. Same sort of thing, actually. It's my video, my in-class video for standard deviation. And that's about it, okay? That's all we need for now is standard deviation, bigger, more spread out. But there are some issues, okay? And we're going to get to that in a bit as we move on into our analysis. All right, thanks.